Cool. Let me just quickly. Yeah, let's make sure the right. Yeah. Cool. Hi, everybody. Thanks for joining us today. I'm really excited to welcome Trevor Campbell here to Madison. Trevor's an associate professor at UBC, and before that, he did a PhD and a postdoc at MIT. And broadly, I think, how would I describe Trevor's interest? Well, I think a lot of it recently is on this sort of like automated and scalable Bayesian computation and Bayesian nonparametrics, and I think we're in for a real treat today. So please welcome Trevor. Alrighty, can everyone hear me? It's kind of a big room, yeah. Well, thanks, Samir, for the invitation to come out. I'm delighted to be out here and get to meet all of you. As promised, today I will be talking about how to automate statistical inference, and specifically Bayesian statistical inference for modern probabilistic models. I should probably start by saying, why do I care about automating statistical inference? For me, so I'm a Bayesian statistician, most of the work that I do falls in the Bayesian paradigm. And Bayesian statistics is sort of inherently automated, right? As long as you're willing to specify a prior distribution that encodes your understanding of your parameters before seeing data, and a likelihood model that captures some realistic data generating mechanism, then probability theory tells you what to do. Right? You combine these things, you get a conditional distribution on your parameter given your data. And so that's great, right? Bayes is automated in theory, but in practice, that's not actually how this shakes out. In practice, you need to sample from that posterior distribution, and that inevitably is going to use some kind of approximation algorithm like Markov chain Monte Carlo, or variational methods, or sequential Monte Carlo. And these things can fail in quite nuanced and sort of tricky ways that even experts struggle with. And practitioners struggle tuning these things as well. And that performance can be quite sensitive to that. So I want a pipeline or a tool set that sort of lets me ignore all the computational stuff and just tell a practitioner, let's design a good model together and then hit go and hopefully results. So anyway, that's kind of the gist. I'll get into some really cool projects that have happened in my lab recently today. But before I get started, let me just acknowledge my collaborators here. Nicola and Miguel are my PhD students. They are both co-supervised with Alex Bouchard, my colleague at UBC. Ivy is my master's student, and Saf is a former PhD student of ours now at Oxford. Okay, what do I mean by modern probabilistic models? I think the best way to illustrate this is with an example. So this is an example that I was involved with a little applied project recently with William Thomson at the University of Victoria. And William is an astronomer. And so William studies exoplanetary systems. And one of his interests in exoplanetary systems is brown dwarfs. So brown dwarfs, this is this sort of middle red blob here. Brown dwarfs are bigger than a planet, but they're too small to fuse their own hydrogen. So they're usually, just for reference, something like 13 to 80 times the mass of Jupiter. So William and his collaborators have noticed that based on their orbits, brown dwarfs, which usually are orbiting some much larger host star, they're a lot dimmer than you would expect from physics. Okay, so based on their orbits, you can tell roughly how heavy they are. Based on how heavy they are in physics, you can tell how bright they should be. And William and collaborators realized that they're quite a bit dimmer than they should be, 2 to 6 times less. So this is one particular system, Gliese 229. Gliese 229a is the host star, that's the big guy here. Gliese 229b is that small brown dwarf that's orbiting. Okay, now, in a very recent Nature paper, William and collaborators discovered something really cool. These brown dwarfs, or at least Gliese 229b, is not actually one brown dwarf, it's 2 brown dwarfs. It's 2 brown dwarfs that are orbiting themselves as they orbit this larger host star. That's crazy, right? So he's got this cool paper. The cool brown dwarf, Gliese 229b, is actually a closed binary. You can see a little plot of that here. The declination and the right ascension, these are sort of angular coordinates in the sky. And you can see the 2 little brown dwarfs sort of in this helical orbit.
So just a question.
Yeah.
The moon goes around the Earth, but the Earth doesn't go around the moon. But you're actually saying these 2 guys are sort of spinning, or is one spinning around the other?
So the Earth does go around the moon.
Oh, does it? Okay.
Just by an imperceptible amount. Because the moon is much less massive than the Earth. Right? So the Earth is actually wobbling just the tiniest amount.
Gotcha.
And these guys are much closer in mass, so they wobble sort of more often.
Excellent. Learned something. Thanks.
And so the methodology, like, okay, so how did they discover this, right? How did they resolve this 1 brown dwarf into 2 brown dwarfs? I mean, this system is, I think, 13 or 20 light years away, something like that, so it's quite far. And it turns out, so we have their methodology published in the Astronomical Journal quite recently, and it's based on the software that I'm going to tell you about today. William and collaborators designed a Bayesian model for this setup. It's quite a nasty Bayesian model. It has various orbital parameters describing the positions of all these the brown dwarfs and the host stars. That has a lot of angular parameters in it. So, you can see a little diagram here. You have things like the inclination, the longitude of the ascending node, the argument of periapsis, right? Like these very weird angular parameters that you don't often see in Bayesian models. The masses of all the objects in that system, the contrast ratio of the objects, so how bright everything is relative to each other. And then there were also some technical parameters built in that captured systemic effects in the telescopes that they were working with. That's the model. The data that they had to work with, it was very limited, only a couple of data points from each of these sources. But they had radio interferometry, which it's a bit complicated, but you combine multiple telescopes, and what it gives you is essentially the Fourier transform of a picture of the night sky, a spatial Fourier transform. So that's already kind of nutty. And then you have this other source of measurement called Doppler spectroscopy, where you look at the color of the system, and if you see the color oscillating, you can tell that because of the Doppler effect, that system is actually moving closer and farther away. Okay, so suffice it to say, this data is weird. The data generating mechanism is weird. The model is weird. And as it turns out, when you combine a bunch of weird stuff together, your posterior looks really weird. Ignore the orange. The orange is some experimentation that we've been doing with a method that doesn't work. The blue is the actual posterior, reasonable set of posterior samples. This is a corner plot. So you're seeing bivariate marginals here in each one of these little panels. This text is way too small to read, but you can see things like, the eccentricity of the orbit, the total mass, parallax, et cetera. So these are the orbital parameters. And what you can see from this is that it's a disaster, right? This posterior is messy. We have weird manifold structures being caused largely by these angular orbital parameters. We have multi-scale behavior, varying scale. These are funnel shapes. So the sort of variance of one parameter depends pretty strongly on another parameter. And we have multimodality. Actually, if you cut off one of these data sources, specifically the Doppler spectroscopy, and you just use the interferometry, you actually get two plausible scientific explanations for what this system is doing. You need to combine both of these heterogeneous sources of data to narrow it down to one. Okay, so as a practical statistician, this is scary. As a computational statistician, I'm a kid in a candy store. This is great, right? This is exactly what I want to study to develop new methodology. So, okay, this problem is super hard, but I'm a statistician. I'm not an astronomer. Yes.
The previous slide.
Yes.
Can you explain what X and Y axes are?
The X and Y axes. Okay, so of all of these different panels, each panel here is a different variable in the model. So there's, I guess 13 or so different variables. I'm not showing you all of them here. And each on the y-axis is another variable, and we're looking at the bivariate marginals for each variable. Okay, so one pair of variables, if I just look at the marginal for those two, it has this weird sort of funnel structure, for example. Yeah. Okay. So as I said, I'm a computational statistician, so I see this problem and I see a fun computational problem, what can we extract from this? What kind of interesting statistical problems can we pull out? First of all, we saw in this previous example that there's multimodality. Now, if I try to perform inference with a multimodal posterior, with a standard MCMC scheme, I am generally speaking going to run into a problem where I get stuck in one mode. Okay, if the modes are close enough, you won't, but there's often modes that are kind of spread apart, and MCMC will tend to fall into one of them. In some problems, this doesn't matter. In this scientific problem, it actually mattered, right? We wanted to find all the plausible explanations for what this system could be. Another thing we saw is varying scale or multi-scale behavior in the target. And if I run a Markov chain on a target that looks like that, I will often not be able to explore into the thin parts of the scale, right? My Markov chain will have a step size that determines kind of how big of a step it takes, and I will get stuck sort of in this wider region. The last kind of structure that we saw is manifolds. So weird sort of subsets of the space that the parameters lie on. And when I run a Markov chain Monte Carlo scheme on a manifold structure, typically what happens is that scheme will wander towards the manifold. It'll sort of attach to the manifold nicely. It'll mix across the manifold nicely, but it won't mix along the manifold well. It'll sort of walk very, very slowly. Okay. In other words, all of these are sort of captures of one basic phenomenon, which is that MCMC methods are designed to explore well locally, but they don't necessarily explore entire structures of posteriors. They don't explore well globally. The other thing worth mentioning is that when you run typical diagnostics in practice, like looking at effective sample size estimates, they will often mislead. So for example, on this problem, this multi-scale problem, an effective sample size diagnostic will tell you that everything is working fine. It will completely not realize that I've missed mass here. Same with this multimodal target, right? So standard estimates at the ESS will lie to you. They'll tell you things are working fine when they're really not. So the question then is, well, the orbital problem that we solved had all these nasty structures, and I've just told you that MCMC struggles with these structures. So how did we solve this interesting scientific problem? I'll also mention later in the talk just a little vignette on manufacturing aircraft wings, curing carbon fiber parts, because I've also been involved with some engineers in a collaboration that we've also used this tool set. Okay, so this talk is going to introduce a couple of tools. The core, sort of central tool, is something called nonreversible parallel tempering. This was not developed by my lab. This is developed in 2001 by a Japanese team led by Okabe. But we recently analyzed the convergence behavior of nonreversible parallel tempering schemes, and we proved some quite, in my opinion, quite beautiful results about the uniformity of NRPT. This method by itself, I'll get into it in a bit, but there's a lot of things that you have to tune to get this to work well. And historically, people didn't know how to tune it, and so it kind of fell out of favor. But we've now developed a couple of technologies, one being variational methods in parallel tempering, and the other being a new kind of Markov kernel that's used in parallel tempering. And these things together make PT a feasible method to use. Not only feasible, sort of highly performant and highly automated for Bayesian inference. All of this stuff comes together into a Julia software package called, it looks like it says pigeons, and our logo is a little pigeon. But if you want to be totally correct, you would pronounce this pigeon. My collaborator, Alex, is from Quebec. He speaks Quebecois French, and he has assured me, and I can't verify this, that pigeon in Quebecois means let's sample. So we thought that was kind of a cute pun, so we've called it pigeon.jl. Okay, there's a little QR code there if you're interested in looking into it. And if you have questions or need help using pigeons, if you happen to want to try it, well, we're happy to help you out. Okay, without further ado, let's get into the technical stuff. First, I'm going to introduce parallel tempering. What is parallel tempering and how does it work? Well, we know that MCMC that targets just your posterior struggles. It can get stuck. It cannot explore the global structure of the target well. Parallel tempering, the gist of it is that you use many distributions. You run MCMC on many distributions. Some of them are easy, some of them are hard. And you use the easy ones to help you explore the hard ones. The way we do that mathematically is we take our target distribution, pi1, so that's a density. Pi1 is a density. Pi naught, and that's with respect to some base measure, it doesn't really matter. Pi naught is a reference distribution that we pick. So this is meant to be easy, this pi naught. Pi1 is going to be hard. Think in your head, pi naught could be like the prior. If you want, it could also be a different Gaussian that you decide on. But in any case, we construct a path of distribution ranging from pi naught to pi1 by raising the two densities to a power 1 minus t and t, for t ranging between 0 and 1. And then we let t range between 0 and 1, and that constructs a path of distributions. We then discretize that path to n plus 1 steps, t naught, t1, all the way up to tn. And then we run a big joint Markov chain that targets all of those distributions. Sounds like I've just made my life harder, right? I'm now just not doing MCMC on one of these, I'm doing MCMC on all of these at the same time. Let's draw a little cartoon. Maybe it'll help you see why this helps. So here's with n equals 3. Here's my reference. That's my easy distribution. I'm showing you density contours here in 2D, so that's like a Gaussian, right? And then as I mutate that distribution towards the target, which is this multimodal nasty thing, you'll see that we have this weird sort of like interpolating path. In your head, you should think of these things as being on top of each other, but I can't draw them on top of each other, so I just draw them side by side on the slide. Okay, but these are all sitting on top of each other. Okay, how do I run PT? Well, the first thing I do, I'm running a joint Markov chain, so I give each one of these a state, theta 1, theta 2, all the way up to theta n. And parallel tempering has two major steps, exploration and communication. Let's talk about exploration first. This is the easy one. With exploration, we're just going to apply a standard MCMC move to each one of these targets totally independently. Okay, so I'll move theta naught to theta naught here. I'll move theta 1 to theta 1, theta 2 to theta 2, and theta n to theta n. Pick your favorite scheme, HMC, Mala, random walk MH, whatever you like. Okay, this is parallelizable super easy to do. As long as you have TMC, you can do this. So that's not so bad. But the secret sauce of parallel tempering, this is where the magic happens, is the communication step. In the communication step, we're going to propose swaps between neighboring chains, neighboring distributions on the path. So check this out. On pi t2, I've got this choke point here, right? It's really hard to explore through this choke point with a standard MCMC method. But if I look at the same spot on pi t1, it's actually not so bad. It's not so choked. In fact, I was able to explore into this lobe of mass without too much trouble. So now if I propose a swap, you'll see that I'm able to take my exploration on the easier target and move it into the harder target. So now I'm moving theta 1 to be theta 2. I'm moving theta 2 to be theta 1. And just a reminder, these are on top of each other. So that theta, the thetas aren't moving. I'm just relabeling them. Okay, so like this theta is the same value as this theta, of course. Okay, so I do a Metropolis-Hastings correction to make sure that I'm still targeting the right joint Markov chain. I accept, and that's the end of the story. Now you can see that I have moved my state successfully into this lobe. Next time I try to swap this state and this state, I might actually move this theta into this little blob here. So this is helping me do global exploration.
But that MH ratio is going to be hard to calculate.
The MH ratio is actually quite easy to calculate. It only depends on the pi 1 and pi naught evaluated at each one of these states.
Don't you need the normalizers for pi 1?
You do not. This is the magic of parallel tempering. It's self-normalized. For simulated tempering, you do need the normalization constants. For parallel tempering, because you're doing swaps, the normalization constants cancel. Yeah. No, very good question. Any other questions?
So sorry, I had to step out for a moment, but I guess maybe you already said. So this is sort of like you're doing homotopy on pies.
What do you mean by homotopy?
Meaning I'm slowly moving from pi 0 to
Yes.
pi target,
Yes.
right?
Yes.
And that's called a homotopy method often in optimization. So is this, I mean, is it ever called like homotopy CMC or something?
I've never heard it used, that language used. It is called, it has a name in statistical physics. It's like ensemble methods or something like that. This has been rediscovered a bunch of different fields. And I should emphasize, this is not something that I've developed. This has been around for quite some years now. Okay, last little detail here is which ones of these am I swapping at any given time? This is where the non-reversibility comes in. As it turns out, doing a deterministic alternation of swaps, so I do all the even pairs and then the odd pairs and then the even pairs and then the odd pairs. I don't just choose them randomly. As it turns out, that results in much better behavior in this algorithm. Okay.
Sorry, George.
Yes.
Just to be clear, so you're actually running this, you're running your chain on this very, like, this product space, and you're preserving detailed balance on the whole
product space.
the whole thing.
Yeah.
And
Which then, of course, gives you the marginal on pi tn.
And I guess part of, maybe to Michael's question, part of why this is, you have a hope of accepting this is because you're just swapping like consecutive pairs, right? It's
Actually, I mean, if the number n here is very large, then these things are very similar. So when you make the swap, you're basically almost doing nothing, right? So then the higher n is, the more you expect to see accepted swaps. But that being said, the higher n is, the longer you need to travel from the reference to the target. Yeah.
Very quick question. What is a typical capital N that one would use?
Very good question. So in my experience on the kinds of like consulting problems that I work on occasionally, 15, 20, I have seen problems up to around 150 needed. I have most, simple problems that you might run into, like benchmarking problems in the literature, 2 or 3 is fine. It varies. It varies, yeah. And I should say the number scales roughly with like square root of the dimension of the problem if you have independent copies. So the dependence on dimension is actually not bad either. Yeah. Okay. Oh, more. Yes.
Can you give some intuition on why the deterministic swap is better than?
Yeah. You will see it a little bit later in the talk, but the essence is that if you do deterministic swapping or deterministic alternation, you get sort of consistent motion from the reference to the target. The swapping results in piecewise linear paths, whereas if you do stochastic alternation, you get Brownian motion. So it takes a lot longer from a sample to get from the reference to the target. Yeah, it speeds up the communication, basically. Okay, so that's parallel tempering. The thing I have not told you is how to make it actually work. Because as it turns out, well, we're doing a lot more stuff. That means we have a lot more stuff to tune. Specifically, we need to pick that reference distribution. As it turns out, that's really important to pick. You can't just do this arbitrarily. We also need to pick all the temperatures. As it turns out, those are also really important, and you cannot just do them arbitrarily. And finally, we need to pick all of these MCMC kernels. For anyone in the audience who has spent time tuning one MCMC kernel, you know how bad of an idea that is, right? That's scary. So we need methods to handle all this stuff if we want PT to be feasible. I can kind of guarantee you that a well-tuned PT implementation is a real powerful algorithm, and a poorly tuned PT implementation is useless. Right? So you really have to nail it. Okay, so this talk is basically how do you nail it, without having to ask your users to do all kinds of crazy things. So we have reference, temperatures, and kernels. Let's start with the kernels. Let's start with exploration. All right, I'm going to restrict myself to the case where my explorers have a step size parameter. So if you're familiar with random walk MH or metropolis adjusted Langevin algorithm, MALA, or HMC, these all have a step size parameter that determine how far away you move in one go. Okay, and too large of a step size means that you reject and you get no movement. That's bad. Too small of a step size means that you accept your steps, but you make really tiny movements. So it works out to be the same. It's bad either way. So they're quite sensitive to the choice of step size. And as we said, in parallel tempering, I don't just need one step size, I need n step sizes. And I can't just choose the same one for all the chains. I have to choose a different one for all the chains, usually because the reference is much more diffuse than the target. The target's usually very concentrated. Even if you're not doing PT and you're just looking at one target, it's often still troublesome to pick a step size. If you have a multi-scale target, you might need a small step size in some parts of your state space and a big step size in other parts of your state space. So ideally, what we would do in a perfect world is I would run MCMC where I get to pick my step size at every iteration. That's very difficult to do well. In particular, it's very easy to break the invariant distribution of the Markov chain. But we have developed this new method called autostep that does exactly this. Let's do a little warm-up, something called involutive MCMC, developed in the early 90s by Luke Tierney. Involutive MCMC is just a generalization of random walk MH, MALA, HMC, just in one consistent framework. So the way this works, this is for a fixed step size. This is just a warm-up. I have my state variable x. I have some auxiliary variable z. Usually this is like a momentum or something like this. And I have an involution. So this is the mass f that is its own inverse. So if I apply f twice, I get back the input. And it has a step size epsilon. Now, how does involutive MCMC work? I resample my auxiliary variable z from some distribution m. Usually m is like a Gaussian. I make an involutive proposal. So I propose to move to x prime z prime using this function f. And then I do my Metropolis-Hastings correction. Okay, and that depends on the familiar density ratio between pi m x prime z prime and pi m x z. And there's a Jacobian term here that you can ignore. In all the examples I'll show you is just one. So you can just
clarify. The involution means if you take two steps, get back to one.
If I do f, and then I do f again, yes, I'll get back to where I was before. However, remember in between, we're resampling that auxiliary. So we actually change that in between each step. Yeah, good question.
Maintain reversibility.
Yes, yeah, exactly. So this step, this is like a Gibbs step, if you want to think of it this way. And then this is the correction that you get to maintain detailed balance. Yeah. Okay, so that's a fixed step size MCMC. How do we turn this into an adaptive step size MCMC? The way we do this in the autostep framework is we start by sampling two probability thresholds, A and B. These are uniform between 0 and 1, and A is constrained to be less than B. And then given the current state, x, z, a, b, we choose a step size epsilon. How do we do that? Well, the intuition is that if I have an acceptance probability of a move, I don't want to be on the left side of this plot here because that's too small. My acceptance probability is 1. I don't want to be on the right side where my acceptance probability is 0. It's too large of a step. I want to be somewhere in the middle here. So what we do is we use this A and B as thresholds that tell us what's an acceptable probability to have. And then I start with a guess, epsilon naught. 1. Doesn't really matter what it is. Okay? And I'm going to say, is epsilon naught a good step size? Well, in this case, my acceptance probability for epsilon naught is almost 1. It's greater than B. And so what I'm going to do is double the step size until it's aggressive enough. So I double it once. It's still too conservative. I double it again. Now my acceptance probability is below that threshold, and I take that as my step size. Okay? If I start with an epsilon naught that's way too far to the right, I divide it by 2 until it comes over to this region. I cannot just do this by itself because this is not maintaining the right stationary distribution. I have to correct for the fact that I picked my step size. And so what we do is something called a reversibility check, where once I use that step size to make a proposal, I compute the step size again at the proposed point, and then I make sure that I would have used the exact same step size going forwards and backwards. If I use the same step size going forwards and backwards, we're good to go. I can do the Metropolis-Hastings correction. If they're different step sizes, I reject immediately.
This sounds kind of like multi-try
It's a little bit.
MCMC.
It is
Is there
indeed.
a connection there? Or?
There is a connection. It's a little bit technical, so I probably won't go into it here, but you are absolutely right. It is connected. Yeah. Yes.
So this looks a lot like elliptical slice sampler.
Yes.
Particularly for Gaussian type of like broad distribution. Is there a connection there, or?
It's a very good question. So the elliptical slice sampler is quite constrained. You have to have a Gaussian component in your target. This does not have such a constraint. I would hesitate to say that they're super connected. I think they're probably not so related. Yeah. But I would need to sit down and maybe think about it for a bit, because sometimes there's sneaky connections in these things. Yeah. Yes, sure.
Similar question, but have you also thought about the relationship between diffusion-based sampling and this one? Because it sounds like there they also have this kind of specific diffusion-based reference model.
Yes.
Which you're sampling.
Yeah. So the big difference is that you can't write down the marginal distribution in closed form along the annealing path in the diffusion models. Here you can, and that's necessary for doing MCMC. You can't do this out of the box with something like a diffusion annealing path.
But there they do the non-UPN sampling, so they just need.
That's right, but they have to approximate the score function, whereas we don't have to do that here. Yeah. All right. So this is sort of just a quick overview of how we do autostep. Let me give you one little result on how it works and what it improves. Because this is just one of 2 or 3 components, I'm not going to dwell too much on this. But let me just show one little result. This is a synthetic case with a 2-dimensional funnel. So the cartoon is here on the top right. The x1 marginal is normal, and the x2 marginal is also normal, but the variance depends on x1. So as I go to the right, the variance blows up. As I go to the left, the variance. What I'll show you here is 2 different MCMC algorithms. Orange is our autostep method. Blue is nuts. On the y-axis, I'm showing you the estimate of that first marginal mean. So x1 mean, which should be 0. Okay, that's the correct answer. And on the horizontal axis, I'm showing you as we increase the difficulty of the funnel. So as we squeeze that neck in and make it harder and harder to explore. What you can see is that autostep is quite robust. As we squeeze that funnel in, the mean estimate hovers still right around 0. In other words, it's able to explore into that funnel because it adjusts the step size on the fly. Nuts, on the other hand, at some point is just simply not able to explore into this thin region, and the mean estimates become very, very biased to the right. Okay, so this is the kind of behavior we want from autostep, this robustness to scale. If I'm in a small scale region, I pick a small step size. If I'm in a large scale region, I pick a large step size. Okay. On the theoretical side for autostep, we verified sort of the basic properties that you would hope for. We know that autostep is pi invariant, it's irreducible, and it's aperiodic under very mild conditions. If you're interested in the conditions, I have a slide on that at the end. The more interesting questions is, well, how much does this cost, this step size selection procedure? We've shown that it terminates after finitely many iterations, almost surely, so that's good. You can actually simulate this process. But more importantly, we have upper bounds on the expectation of the number of doubling and halving steps that you need, which tells you how expensive it is to run autostep. Now, the actual bound that we have here is kind of nasty to look at, so it's not worth going into for a talk. But there is a corollary that I think is quite nice. If I'm willing to assume that my target is strongly concave and Lipschitz smooth, then I can tell you that the expected number of doubling and halving steps scales like the absolute value of log of that initial step size guess. What does that tell me? That tells me that if I'm horribly wrong with tuning that epsilon naught, I pick orders of magnitude wrong for epsilon naught, I still don't pay that much. I pay at most a log. If I do a little bit of napkin math, what this tells me is that autostep will give me an effective sample size per unit cost of about 1 over absolute value log epsilon. And compare this to a fixed step size MCMC scheme like HMC, MALA, random walk MH, which again, if you just do a little bit of napkin math, you'll see on that kind of target, I get the order of exponential of minus absolute value log epsilon. So in other words, we have an exponential improvement in efficiency. We have a little empirical result to demonstrate this. So on the vertical axis here, I'm showing you the effective sample size per unit cost on a couple of targets, normal, Laplace, and cheap. And I have in orange a fixed step size, Metropolis adjusted Langevin algorithm. And in blue, I have the autostep version of Metropolis adjusted Langevin algorithm. And what you can see here is that, yeah, if you tune the fixed step size method well on these targets that don't have multi-scale behavior, you will slightly outperform autostep. And if you mistune it, you are in big trouble, even by a little bit. That performance falls off super quick. Whereas autostep is very robust. It kind of just doesn't care about the tuning of epsilon. And that's exactly what we want in parallel tempering, where we can't really guarantee perfect tuning on all of the chains. Okay, so that's for the exploration. The answer to that is use autostep. That's exploration. Let's talk now about the communication side of parallel tempering, right? Because we still have to analyze what the reference does. We still have to analyze what the temperatures do to the performance. The first question that we should ask is, how do we even characterize the performance of communication in parallel tempering? And this is actually getting back to your earlier question about why we use deterministic even-odd swaps. If I take my example that I've been showing you with these four little distributions, the circle and then the mutate, and then the target here, and I turn it on its side, and I just plot the chain number. So the reference is 0, going all the way up to the target, we have 30. So I guess this is an example with n equals 30. And instead of worrying about where the x's go, where the thetas go, the state variable, let me just look at where the swapping goes. So if I plot the index, the chain index of the state as it gets moved around by the swapping procedure, I do it for all the states, I'll get this weird lattice-looking thing of all these traces. Let me just highlight one of them for you. So this is the one that starts at, what do you think, 13, something like that? It starts by moving itself towards the reference, and then it bounces again, and it hits the reference. It comes back towards the target, comes back down, and then it hits the reference, and it does a big traversal to the target. This linear-ish looking behavior, this piecewise constant velocity, that comes from that deterministic even-odd swap scheme. If I showed you this figure for the stochastic swapping scheme, you would see much more like Brownian motion kind of behavior. But the important thing here is that kind of motion. I want to see a sample that starts at the reference, where I get an IID draw, to the target, where it then presumably sort of refreshes the information at the target. We call these things restarts. We want to get lots of restarts. That means the communication is working well in parallel. Okay, that's a restart. How do I analyze restarts mathematically? It's really, really hard unless you make two assumptions. If you make two assumptions, life gets nice. So we're going to make those two assumptions. The first is that I get independent draws from that reference, that pi naught. That's okay. I picked the reference, so let me just pick it to be something that I can sample from, a Gaussian. That's not a big deal. The assumption that is a big deal is what's called the efficient local exploration hypothesis. Let's parse this one for a second. What this assumption says is that if I take a draw from my exploration kernel at chain n, starting at x, and I move to x prime, that implies that this energy function, this log density ratio between my reference and my target, is independent. That is a strong assumption, right? In fact, I would hesitate to say that that ever holds in practice. But it is a pretty darn good model for what you see in a lot of problems. So if I'm sampling on a manifold, let's say, I'm moving across the manifold really quickly, my energy function is mixing really quickly. Even though I'm wandering very slowly on the actual state space, that V function is mixing very, very quickly. So you can treat this as sort of a model for what we see when we run parallel tempering. This is not actually an assumption that I expect to be true for any given problem. But if you're willing to take this leap of faith with me, what this does is it lets us decouple the analysis of exploration and communication. It delinks them completely because the swapping only depends on the V's. So I can now just completely ignore my kernels and just pretend I have independent draws of the V's at every iteration and look at what the index process does in that case. If I make that assumption, I get this really nice theorem. The restart rate, remember we want lots of restarts, the rate at which you get restarts is given by 1/2 plus 2 lambda n, where lambda n is this n-chain global communication barrier. Rn here is the swap rejection probability for chain n and n plus 1. So how likely am I to reject that swap? That's Rn. Lambda n is the sum of all the Rn's divided by 1 minus Rn. Just maybe playing with this formula a little bit for a second. If any one of my Rn's, my rejections, are close to 1, that means there's like a choke point in my swapping procedure. This lambda n screams off to infinity. So I really want all of my RNs to be low, all of them, not most of them. I want all of them to be as low as possible. Okay, so in order to maximize the number of restarts in parallel tempering, we want to minimize this n-chain global communication barrier. That's our new objective function. Maybe one little side discussion about that global communication barrier is, well, if you're an MCMC practitioner, what you care about is geometric ergodicity or uniform ergodicity, right? What is the convergence of that Markov chain to your actual target? It turns out that you can do an analysis in the large chain limit that tells you a lot about how these things are related. What is the large chain limit? If I take the number of chains to infinity, which sounds totally crazy, you would never do this in practice, right? Like this is asking for infinite number of GPUs to run your parallel tempering. Okay, it's a bit silly. But the point is that, again, this is a good model for what we see in reality. In particular, the error term here is 1 over n squared. So this convergence happens super quick. In practice, I see this reasonable behavior with n equals 10, 20, that kind of thing. If I'm willing to work in asymptopia, I have a result here that summarizes 100 pages of math in one slide. This is the geometric ergodicity. It's actually uniform geometric ergodicity of parallel tempering. Okay, let's parse this result out for a second. It says in the infinite chain limit, if I look at that marginal target chain of my big MCMC procedure after nk iterations, the distance between that distribution and my target is bounded above by c, which is a constant. And I have a formula for c. I can try to numerically evaluate it. We get about 1.2. In practice, it's about 1.2. Our best theoretical upper bound is 106. You know, it's not like one of those geometric ergodicity results where the c is like 10 to the 43, right? It's 100. Okay, it's not too bad.
And just clarify, so when n is large, you're going to be spending relatively little time in the target. So is that a problem?
Well, always a chain running in the target.
Always a chain
Right.
Target. I'm thinking simulated temperature.
You're thinking simulated. And in fact, actually, keep in mind that we're running this big ensemble. If the communication is happening well, every iteration, you're getting a refreshment into that target, right? So it's almost like you're getting independent draws. It's just that it takes a long time for those draws to get from the reference to the. Yeah.
And why can you do only neighboring swaps?
This is an excellent question. You can do other things as well.
Yeah.
As it turns out, neighboring swaps alone make the analysis, or it is a regime in which you can analyze the behavior. It becomes sort of like you can analyze like a stochastic process, basically. I'm not aware of a lot of literature that does more complicated swaps, generally because it just seems like it hasn't been worth it. But I could see an advantage in some cases where you're allowed to make these much bigger moves. It's just that the distributions don't tend to align very well.
Yeah, then you reject more often. Right?
You reject, right? So you end up spending a lot of work that isn't super useful. Yeah, so the neighboring swaps are like the safest ones to do in some sense. Yeah. All right. Okay, so forget the constant. The important thing is this rate. It's e to the minus k, that's the number of iterations, divided by lambda. There's that global communication barrier. So what this tells you is that the restart rate, the GCB, and the rate of ergodicity, the rate of total variation convergence are all linked to each other. I would love to tell you more about the theory behind this. It's absolutely beautiful, complex analysis. It's super, super in-depth. I don't think I have time to go into any of it today, sadly. So you'll just have to take my word for it. It's really cool. If you want to ask me about it, I'd be happy to discuss it. That's this paper, Uniform Ergodicity of Parallel Tempering with Efficient Local Exploration, which has been submitted. Okay.
Sorry, Trevor.
Yes.
Just to maybe drill on this a little bit. So
Sure.
that lambda is really dictated by the communication.
The lambda is dictated, you can think of it like a KL divergence. Lambda is actually a divergence between pi naught and pi 1.
I see.
There's a formula for it that I'm not going to write down. It's an integral of
But it is the limit of these like lambda n's, which is really about how you're swapping states.
It characterizes the trade-off. So of course, as n grows, of course, the distributions are getting closer. So the rejection rates are going down. But as n grows, there's more n to make.
Right.
So there's a trade-off there, and that lambda captures that trade-off.
But is this going to assume that I'm like geometrically ergodic on each of my states?
No, in fact, you don't even have to be irreducible. You can be reducible on each of the chains. Yeah. No, PT does some pretty crazy stuff. Yeah.
Okay.
We can talk about an example about this later. Yeah. That efficient local exploration assumption, it is strong in some ways, and it's very weak in other ways. Like, as I said, you could have a Markov chain that literally never mixes between two regions of state space, and PT can fix that for you. Kind of interesting. Okay. Suffice it to say that lambda is the right objective function to minimize. So how do we tune the temperatures and how do we tune the reference distribution by minimizing lambda? So just a reminder, our n-chain global communication barrier, the finite chain version is up here. The intuition here is that to tune the temperatures, I want to make sure that all of my restart rate, rejection probabilities are small. I don't want one to be a choke point, right? And the problem is when you start, you're going to start with evenly spaced temperatures, which leads to imbalanced rejections, which leads to there being one big rejection rate where the distributions don't overlap very well. Okay, so no swaps are going to make it past that point. You're going to get no restarts. PT's not really helping you at that point. What you want instead is to use unevenly spaced temperatures, which then give you balanced rejections, which means that you have usually a slightly larger rejection rate everywhere else, but the maximum, the worst case rejection rate is small. Saf, in his earlier work, proved that this actually minimizes that finite chain global communication barrier. So you want to have even, it's called equi-rejection. You want all the rejection probabilities to be equal. And the way we do that, sort of succinctly, is we just try some temperatures. We start with evenly spaced temperatures. We run parallel tempering. We collect those rejection probabilities. One of them will probably be terrible. That's okay. But we readjust the temperatures after that to try to place them where it would be such that we think the rejection rates will be equal. And if you keep doing that and you take more and more samples, we find in practice that very quickly this method stabilizes around a very good set of temperatures that do give you equi-rejection. So that's fairly straightforward. And that, I should say, this is not my work. This is Saf and Alex from a couple years ago. They're the ones that figure out how to tune the temperature. The other piece of communication is the reference distribution. So we know how to tune the temperatures. How do we tune the reference? Well, again, we want to make that global communication barrier small. We want to maximize the number of accepted swaps we have, which means we want to maximize how overlapped all these distributions are. If I have a pi naught and a pi 1 that are very different, I'll have not much overlap. I'll reject all my swaps. I'll have a low restart rate. I'll have a high global communication barrier. If I can somehow make that pi naught close to pi 1, then I'll have a lot more overlap. My swaps will be accepted. I'll have a low global communication barrier. Actually, I can reduce n typically when this happens, right? Because I don't need to have so many distributions on my path. I can take sort of bigger leaps. The idea here is this is variational parallel tempering. The idea is instead of using pi naught, setting it to say the prior, which is what people typically did in the literature, let's set it to a tunable family, Q phi, where phi are some tuning parameters, and we'll use that in our parallel tempering path instead. It's a very simple idea, but it's actually an incredibly effective one. Under one condition. We don't want to have any user tuning, so gradient methods are out, right? Because gradient methods require you to pick a step size, and I don't want my users to have to pick n step sizes, but thank you. Or I guess in this case, it'd just be one. And all we need from this is a quick and decent fit. I don't need my variational family to be perfect here, because my annealing will take care of that. My parallel tempering will fix any sort of mismatch that I have. So I just need something reasonable. And if you need a distribution that fits another in a reasonable sort of okay way, why not just use a Gaussian? So in orange, I'm showing you an okay fit to all of these three problems, right? I've got this nasty multi-scale thing. I've got my multimodal thing. I've got my manifold thing. And here's just a Gaussian that does okay. It kind of covers all the mass, which is what you want. It doesn't have to be perfect. The point is that sampling from this Gaussian reference will let you explore the global structure of this target quickly. Parallel tempering will sort out the details for you. Okay, so we do this with a Gaussian, and we fit the Gaussian with moment matching. Just estimate the mean using samples from PT, estimate the variance using samples from PT. There you go, there's your Gaussian. No gradient tuning required. We have a couple of theorems about this. I'll just present one little sketch here for fun. If your model has what I call a Bernstein von Mises-like posterior, so there's some technical conditions here. Basically, you just need your posterior to concentrate around a true parameter, and it should look like a Gaussian as long as you get enough data. As the amount of data points goes to infinity, if you did the thing that existed in the literature, you just use that fixed reference distribution, that lambda, that global communication barrier, is going to scream off to infinity. So your PT becomes completely ineffective. On the other hand, if you just do this silly little Gaussian fit, your global communication barrier will converge to 0. Got about 10 minutes left, 7 minutes, something like that. Perfect. Okay. So this gives you justification, right? Yes?
Does there exist the optimal large n?
Does there exist an optimal large n? Yes, there does. That's a very good question. The question is there a optimal setting of the number of chains. I won't get into it too much, but the answer is basically set n proportional to lambda. Whatever your value of lambda is, you want n to be about that much. And in fact, when n exceeds that, you're kind of wasting time, right? You're getting enough swaps anyway. And so what you should do is actually do parallel tempering. Use multiple copies of PT. So if you have any extra compute on hand, if you have like 1,000 GPUs and lambda's 10, okay, set n to 20 or something like that, and then just do 50 copies of PT. Right? Yeah, good question. But that gets into like the non-asymptotic analysis of PT, so it's a bit trickier to analyze. Yes.
So you're not doing the usual variational, right? Because you want the mass coverage.
Yes.
Right?
So the moment matching in the Gaussian is actually in any exponential family is equivalent to minimizing the forward tail. So it gives you the mass covering. Standard variational inference gives you mode seeking. So that reverse KL, and that's not what you want, right? You don't want a tiny little Gaussian that sits right here. You really want this Gaussian to cover the whole distribution. Yeah, good question. Yes.
Does your optimal capital N change over time? Also the so basically the temperature tuning, would you want to shift it?
So this is a great question. The optimal capital N does change as you tune, because as you tune Q phi, your lambda is going down, right? Because you're getting a better and better path. Yeah. And so then the number of chains you need goes down. Yeah. So absolutely, yeah. And actually Pigeons does not do that yet. That's sort of a project that we want to do this summer is sort of adapt N over time. Yeah, good question.
This prior to could change.
The prior doesn't matter as much because actually the Bayesian prior is all looped into this target, right? Actually, pi naught, it's kind of unfortunate notation. Pi naught is not necessarily the prior. It's just that in the literature, people always use the prior because what else are you going to use? Now that variational inference is a thing, people know that, oh, yeah, maybe we can actually tune these distributions. And it turns out that there's much better choices than the prior. In fact, arbitrarily better choices than the prior, right? Yeah, super. All right. So here is the final algorithm. We've got autostep, we've got temperature tuning, and we've got variational reference tuning. The way we're going to do this is we're going to run parallel tempering in an inner loop in rounds, okay? We will start by initializing our variational parameters to anything. I don't care, standard Gaussian, fine. We're going to start picking evenly spaced temperatures, easy. We will start by using that initial step size guess to just be 1 for all the autostep explorers. Fine. Then we're going to run rounds. In each round, I'm going to take 2 to the R draws with parallel tempering, using the current path and using the current temperatures and using the current autostep initial step sizes. Okay. I'm then going to use those draws to tune in closed form the new set of temperatures via that equity rejection criterion, the variational reference via moment matching, and the autostep initial step sizes, epsilon, and I haven't told you this yet. We're just going to look at the median of the step sizes that we tried to pick when we were running autostep in the previous round. Okay. So you'll notice there's no user input here at all. The user never has to say anything. In fact, as long as they're willing to design a probabilistic model, they can pass it off to Pigeons, and Pigeons will just do this. So this to me is a very, very compelling framework for doing Bayesian inference. The one thing that's not automated here is N, choosing N, which you still have to do. But I think that there are automated ways of doing that, and we're working on that this summer.
Can I just ask a quick question? Yeah. Maybe everybody else understands, but so this Gaussian reference, you need to have moments and covariance or whatever of the target. Is that easy to come by?
Yeah. So if your target does not have a finite second moment, say, you're kind of in trouble, right?
And then my next question is like, can't lambda, you said, well, maybe lambda's 10, but why wouldn't lambda be like 10 million in some cases? Like if I have a really nasty target.
Yeah. No,
so
it's certainly
I'm just trying to understand, like, when will I have, in the problems you were talking, the applications, are these all cases where I'll have a nice lambda value?
So Saf, in one of his earlier papers, had a gigantic table of like many problems across many domains, pulled out of literature, sort of at random, and all of the lambda values were less than 50. I have struggled to find problems with a larger lambda value. I have seen one in a Bayesian non-parametrics problem where lambda was 150. That's the biggest I've ever seen.
And what kind of dimensional space?
That was like 10,000. It was insane. It was super high dimension, right? The dimension scaling of lambda is root D. If you have an IID product, so it does scale reasonably well with dimension. Yeah.
Cool. Thanks.
Yep. Okay. So that's yes.
You mentioned dimensional scale. What would you say the upper limit of dimensional scale for this approach is?
I haven't found it. As long as you have enough computation, as long as you can set n large enough, you can make that spacing between those distributions small enough, you're good. You get swaps. Yeah, honestly, I truly haven't found it yet. And I use this, as I said, in like real consulting problems with all kinds of crazy models and data, real sort of scientific applications. I truly haven't found the upper limit yet. It doesn't work perfectly on everything. Of course, that would be crazy to say that. It's not a panacea. But it's the best thing I've found, the most sort of generally applicable thing. Yeah.
At the risk of being pedantic, doesn't the user still need to specify a Markov kernel? Or are you just going to use like Mala or
so indeed. No, you're totally right. They do have to pick a involution.
Okay.
Sure. Once you pick an involution, you can autostep.
Right.
So they could pick the random walk MH involution. They could pick the Mala involution. They could pick the HMC involution. Indeed, yes, they do have to pick that. In a lot of our experiments, we've just been using Mala because it's simple, straightforward. Yeah. Okay. So that is the final algorithm. That is the whole thing. That's what's running in pigeons. Here's a cute little example, and we'll wrap up in just a minute or two here. This is from that composites manufacturing problem I promised at the beginning of the talk. I have some engineering collaborators in material science, and they are very interested in making aircraft wings. The way this works is you take some wet carbon fiber that is pre-pregnant. It's sort of soaked in resin that cures, and it cures in an autoclave, which is a super high temperature and high pressure oven, more or less. And the problem is that sensing the state of the part at hooks is really important for safety reasons. And the way that they can do this is with very crude sensors because they have to survive in the autoclave. So they have what are called thermocouples, which are very crude point temperature sensors. And they can't put them even on the part because that would destroy the part. They have to put them sort of nearby the part in the autoclave. So suffice it to say that they have this crazy differential equation that's running, and they get some very, very bad sort of point measurements over time, very noisy point measurements over time of the process. This is another one of these very nasty posterior distributions that shows up. But this is a little, zero-dimensional cute simplification of it. I'll show how this algorithm works on this example, because I think this basically tells you the whole story. You don't need too many more results than this. On the vertical axis here, I'm showing you the number of restarts that you're getting from this variational PT scheme. On the horizontal axis, I'm showing you the number of iterations. Of course, higher here is better. You want more restarts. And I've split the algorithm into different pieces. So I've got a baseline where we're not tuning anything. I've got a baseline in green where we're tuning only the temperatures. I've got a baseline where we're tuning only the variational reference. And then I've got variational PT at the top in blue. The figure is pretty clear. There's one line that gives you a restart, right? And that's variational parallel tempering. In particular, it's critically important, and I found this as well in a wide variety of problems. You have to tune everything to get PT to work. If you don't tune everything, it will fail. But if you do tune everything, it's really quite useful. One more thing worth mentioning is that point there where it starts to help is round 6. So round 6 is like 2 to the 7 draws, which is what, 128 or something like that. So after about 128 steps of this Markov chain, it's tuned fully. It's giving you a benefit. Right, so the tuning procedure that I proposed is very, very stable. We have some other figures in the papers that show just how stable it is, but suffice it to say that this is a pretty usual result. It tunes quite quickly. We've tried this across a whole bunch of different problems. The story is basically the same across GLMs, unidentifiable models, ODE parameter estimation, mixture models. Have fun, design whatever you like. That problem that I showed you on the previous slide is a truly hard problem. We've tried it on a lot of easier problems where you do get restarts from the baseline PT. This is with temperature tuning, so all of these have temperature tuning. If you don't do temperature tuning, you're basically nothing's going to work ever. But this is with the no reference tuning, so blue is just using the prior. Green is using a full rank Gaussian approximation, and red is using the diagonal Gaussian. And you can see about what you'd expect, right? A better variational approximation gives you slightly more restarts. But for my money, the order D computation that you need from the diagonal Gaussian is about as good as I would want compared to the, let's say, D cubed plus D squared per iteration computation from the green line. Okay, but this story basically holds true across pretty much every example we've looked at. I think for time reasons, just to leave some more room for questions at the end, I will wrap up there. I do have some more results if you want to see them, but we can get into that as the case may be. The point of this talk, I think my big sort of takeaway is that parallel tempering is one of the few things that works across a super huge variety of problems, but it's really sensitive to tuning. So if you can come up with a good tuning procedure, PT becomes your favorite tool ever. If you can't tune it well, it's quite troublesome. And so this talk was fully automated methods for tuning all the things you would want to tune in parallel tempering. In particular, temperature tuning, that again was not work by me, that was by Saf and Alex back in 2022. There we're just minimizing the worst case swap rejection rates by setting them all equal to each other. Reference tuning, that's that variational parallel tempering paper from a couple years ago. We do forward KL minimization via moment matching and exponential families. And finally, for tuning the explorers, we used automated locally adaptive methods. One example of this is autostep, that paper that I told you guys about earlier. And finally, just for fun, we did work on some convergence theory for all of this, and that's that annals by probability submission that is on. There's, again, the link to Pigeons if you're interested in trying it. And with that, I will thank you for your time.
So when you're doing the reverse scale, so your moment matching, are you using like a cavity-based approach, or I mean, you need to know the posterior moment, right? I mean, it's kind of like a chicken egg problem.
It is a chicken and egg problem. That's why we do this round-based tuning. So in the first round, you get, okay, really, you don't do round one with 2 draws. You do round one with 32 draws or something like that, and you get a pretty bad estimate of your posterior, for sure. But it's slightly better than the previous one. So then you run another round with even more draws, and you do even better. And at some point, this thing stabilizes. The thing I didn't tell you is that we actually run parallel tempering in a V configuration. So I showed you parallel tempering in a line, right? A one annealing. But it turns out that if you're unlucky, those early draws can cause you to get into a weird, bad estimate of your reference. So we maintain one leg to the prior, which no matter how badly things are going, it will still be at least as good as it was at the beginning. Eventually, that will fix the draws, and then you get it better. Yeah. So we stabilize it with a piece of yeah.
And how do you convince yourself curious that you get better?
How do I convince all?
So that's the reason.
How do I convince myself that posteriors are good? If you have a good method for that, let me know, because I really struggle with this. I mean, the only tool that I'm aware of, well, there's a couple of things that one can use, but they all kind of boil down to something like an estimate of the effective sample size. That is just a notorious. It's just really, the best you can do is claim that your samples look almost independent, but you can't claim that they're a good approximation.
Yeah.
Cut the test out.
It already came up as a question in the first plot with the blue margin.
Yeah.
So is that sample viewing options?
So there might even be stuff that we're missing.
Yeah.
But I mean, suffice it to say that it found at least that stuff. So that's better than anything else we've tried.
Sure.
But no, it's a very valid point. Like diagnosing whether MCMC is actually giving you a good answer is ridiculous. I don't know if anything.
Let's thank Trevor again.
I really enjoyed it.
Yeah.